So the next topic on our agenda is going to be discussions about ionization energies. So that kind of wraps in with the photoelectron spectroscopy. Let's remind ourselves what ionization energy is. It is the amount of energy you need to add to remove the least tightly held. So I'm going to add some energy to an element, and I'm going to remove a valence electron. That's the first ionization energy. So when you've got an atom and you're going to remove an electron, that's going to be what we consider ionization energy. Now, if you remember, as you go across the period on the periodic table of the elements, so for example, lithium all the way over to fluorine, the ionization energy increases. You have to spend more energy to get valence electrons away from nonmetals than you do metals. Metals are happy to give them up, so it doesn't take much energy. Go over. Fluorine has the highest ionization energy, the highest electronegativity. He's super small, and he's really good at taking other people's electrons. Now, a lot of times when we're talking about trends on the periodic table of the elements, we ignore the noble gases because they don't always follow the trends, because they're totally non-reactive. Well, ionization energy is one where you can talk about noble gases. We expect them to have high ionization energies because they don't want to give up any electrons. They don't want to take any electrons either. So it is going to cost you a lot of energy to get the electrons away from a noble gas. The larger and more metallic an element is, the more likely it is to give up valence electrons. It will gladly give them away. That's the first ionization energy. The second ionization energy was how much energy you'd have to add to remove the second electron. So this guy's already missing one electron. It would be how much energy we have to spend to grab a second electron away from him, and so on and so forth. So that's what we refer to as the first ionization energy, the second ionization energy, and it can go all the way on. Third ionization energy is just how much energy you have to spend to take the third valence electron away. So let's break this down. You see hydrogen only has one valence electron, and it has only the first ionization energy. That makes sense, right? Look at this. As you go on, helium has a very high ionization energy. He doesn't want to give up his valence electrons. Now let's go to lithium. Look at what happens to the ionization energies. The first ionization energy here is very low. That's because lithium has one valence electron that he will gladly give up. But then the second ionization energy and the third ionization energy are super high. That's because those are core electrons. Now let's go to beryllium. Notice the first and the second are pretty low. And then to get that third electron off, you have to spend lots of energy. So you can see that as you analyze the ionization energies, you can actually identify what element we're talking about because you're looking for that huge jump. So with boron, you've got 800, 2400, 3600, then 3600. They're going up in predictable amounts. And what you're looking for is this huge jump. So the red ones are valence, the ones I circled in red are valence electrons. The ones I circled in blue are core electrons. For carbon, notice the first four come up with just a little bit of an increase in energy, but it's that fifth one with a huge jump, like such. So on the AP exam, they will ask you a question. Well, they'll give you the successive ionization energies, and they'll say something like, it's in the third principal energy level. So they'll give you a list, and they won't tell you what element you're talking about. So what you're looking for, and I give you practice problems from the AP exam, what you're looking for is that huge jump to tell you how many valence electrons a substance has or an element has. So this is what we mean by successive ionization energies. We can determine the amount of valence electrons an atom has based on these successive ionization energies and whether you're taking off valence electrons or we're digging into the core. Okay, we're going to continue our discussion about ionization energies. So let's just use the second principal energy level as an example. So in the second principal energy level, you've got lithium first. I'm going to draw you the box diagram for lithium. So lithium has 3 electrons. The 1s sublevel is going to be full, and the 2s has 1 electron in them. Beryllium. So the 1s is full for beryllium, and so is the 2s. Next is boron, and then carbon. Now let's remember, when I'm going to add that second electron to the 2p sublevel, it's not going to go in this first box. Remember, because of Hund's rule, everybody gets 1 before anybody gets 2. Each of the sublevels singly occupied. And then it's at oxygen where we start to double up those electrons in the 2p, like such. So oxygen, next is fluorine and neon. Neon's is ending the principal energy level, so he's got no valence electrons or 8 valence electrons. Doesn't matter how you say it, it means the same thing. So remember, lithium is going to have a first ionization energy that is very low, and its second ionization energy will have that huge jump. Beryllium will have the first and second ionization energy be predictably low. It's not till I get to that third one where it's going to get the huge jump. Now, let's look at boron. The first ionization energy is actually going to be not predictable. We're going to run into exceptions to this rule. So there's going to be a couple exceptions, and one of them is going to be this. This electron is going to come off with a little bit easier than this one. And the reason for that is this singly occupied 2p sublevel takes less energy to pull that first lone electron off. You can also go here, and this is actually a more stable arrangement than this. So we're going to get a little dip in the ionization energy here for oxygen. That is going to be an exception to the increasing ionization energy. So this electron here is going to come off with a little less energy than this electron here. That's where that dip comes from. Because now in oxygen, the electrons are starting to double up, so they'll have electron-electron repulsion. So you're going to see a little bit of an exception to the trend, just a little bit. Remember, when we talk about trends on the periodic table of the elements, they are not hard, fast rules. So some things are hard, fast rules. As you go across a period, the number of protons in the nucleus is going to increase. That's a hard, fast rule. But the ionization energy is going to have a little bit of an exception because of those odd arrangements there. And that's what your assignment today is going to be related to, trying to understand the exceptions to the rules. They typically do ask something like that on the AP exam, something that indicates that you understand where those exceptions come from. Here is a graph of said ionization energy versus atomic number. So as expected, the ionization energy of the noble gases here, this noble gas is atomic number 10 of neon. As expected, the ionization energies are going to be high. The reason for this is they have complete electron shells. They don't want to give up any electrons, and they don't want to take any electrons. So therefore, they have no electronegativity values because they don't try to take electrons from somebody else. And they have high ionization energies because they don't want to give up their electrons. So actually, even though noble gases do not participate in a lot of the trends, they do participate in the ionization energy one. So here's number 2. Then we go down here is our alkali metals. They have the lowest ionization energy of their family. So you've got lithium down here, and it's going to increase. The ionization energy will increase until you get to the noble gas at the end, which is neon. Now, the exception to the trend that I just explained is illustrated here. So after lithium, you have beryllium. This is going to be beryllium. And then the next one, which is a little bit of a dip and a deviation from the trend, is going to be boron because that's the double up. Because that's the first electron in the 2p sublevel. So it comes off with a little bit more ease, a little less energy than the doubly occupied 2s electron shell of beryllium. Then the next deviation here is right down here. This is nitrogen, where there is one electron in each of the orbitals in the 2p sublevel. They're evenly spaced out. Oxygen here is the first orbital getting doubled up with electrons, and that electron-electron repulsion is what is responsible for the deviation from the trend in that. So as you go across a period, you expect for the ionization energy to increase from left to right. So the first principal energy level, it should increase as you go across the second principal energy level. Lithium through neon, it'll increase as you go across with a couple exceptions that I explained. And then sodium through argon, which is my next set here, you can see those exceptions appear again. Again, when the first electron in the 2p sublevel is placed, and then when the fourth electron in the 2p sublevel is placed in the first one to be doubled up. Notice when you get down here, all this messy stuff here, those are going to be your transition elements that don't necessarily follow the trends either. Remember, when we talk about trends, we're always talking about the representative elements or the elements from the S and P blocks. Those are the valence electrons of any atom. The D and the F subblock, which are the transition elements, are not valence electrons.